Okay, well, once again, we're going to say good evening to everybody and welcome to our webinar on the Aurora Borealis or Northern Lights. I think you're familiar with the two of us. I'm Joe Delicarpini, the Science and Operations Officer, and with us is Bryce Williams, one of our esteemed meteorologists who will take us through this presentation tonight. I'm Bryce, I don't know as much as you do about this, so that's why we hired you. You're a smart guy. So
Oh,
you can
thanks,
take
Joe.
us through. I surround myself with smart people on these webinars. So uh, Bryce, I will hand it over to you, and then I'll be back to help answer questions, and then I'll also be giving our weather briefing for tonight. So, Bryce, I will let you take it from here. Oh, we don't have access for the video.
Oh, that's too bad. Well, I'll just have to
Okay.
describe it.
I'll go
It's
to the next
well,
slide, and you can describe.
yeah, you can do it next slide because it was just a video of the Aurora that I was gonna have playing while I talked, kind of did a little intro. So, um, basically, we got a request for an Aurora video a couple months ago, and Joe, you said I'm smart, but to be honest, I learned a lot while I was making this video because there's a lot that I didn't know about the Aurora. I have been fortunate enough to see the Aurora myself. This picture on the bottom in the middle is actually my picture. When I was working as a meteorologist at our Spokane, Washington office, and I was on a night shift. And so this is the building in the foreground there is we call the upper air building. That's where we prepare our weather balloons to launch. And so when I was preparing the weather balloon one morning, the Aurora showed up, and it was really, really neat to see. It wasn't strong enough for me to see the things that we sometimes see, which it was in the video I wanted to show of the Aurora kind of dancing around and moving, but it was a awe-inspiring experience nonetheless. So hopefully some of you have gotten the privilege of seeing it, or you will one day, because it's just awesome. And these are some more pictures, and we'll talk about why we can get different colors. In the top right, you can see a little bit of purple with the green, and then the top left one's a little more aqua. You get some red sometimes. Actually, in the next slide, we have pictures of more red and purple aurora, and these actually come from Rhode Island. One of our webinar attendees emailed us these pictures. Ronald Zinconi, hopefully I hope, sorry if I mispronounced your name, but was kind enough to send these pictures they took in Rhode Island several years ago. I want to say it was a decade or so ago. So we do get the aurora this far south. It's much more few and far between than our neighbors to the north, but and neighbors that are farther away from big cities with lots of light pollution, but we do get to enjoy it sometimes. So let's go on to the next one and see. So I just wanted to show a little animation, a sneak preview of what we'll talk a little bit more about what we'll talk about later. But this is an animation, a simulation of an actual Aurora Borealis event back from 2012. And so it's kind of cool just to see how it progresses and becomes visible and then invisible as the sunrise and sunset moves around the globe. And you can see this event looks like it probably didn't impact New England because it wasn't far enough south. But when we do have those, you'll see these dip even further south in latitude. All right, so to kind of start us off, what is the Aurora Borealis, or the Northern Lights as we call them? So Aurora is actually just a name given to this glow or this light that gets produced. The thing that's producing it is electrons from outer space that are coming down into the Earth's magnetic field, colliding with atoms in the upper atmosphere, and it forms in a ring, like we saw in that last video, around the poles of the Earth, or a ring or an oval, a ring-type shape. And actually something I think we'll talk about this later, but something I learned that I didn't realize was when you get a aurora in the north, you also get a matching aurora on the southern pole. And so that's kind of cool on both poles. And so these collisions of these electrons with the magnetic field produce light, kind of like we get light through with a neon gas in those blinking neon lights you see outside of restaurants or stores. It's the same kind of phenomenon, just electrons and molecules colliding together, producing different types of colors, and we've just harnessed a similar thing for those neon lights. So the name, actually, this was an interesting thing I actually didn't realize, what the name for the northern lights is different than the phenomena in the south. So in the northern hemisphere, this is called the Aurora borealis, which is what vast majority of people here know it as. But if you were in the southern hemisphere, they call theirs the Aurora australis, or the southern lights. And so the name Aurora was first used by Galileo. It comes from a Latin root, Aurora being the goddess of dawn. And then the word borealis also is a Latin root, comes from the Latin word boreal, which means northern or from the north, whereas australis is Latin for austral, which means southern. So makes sense. Okay, so a little bit deeper into what causes the aurora. So, and this slide, more than maybe any of the others, is one where if you have many really deep questions about these, I may have to say I'll get back to you, because this is where we start to get into some of the things that I learned as I was making this presentation. And just a side note here, so the Aurora borealis, and predicting that is, it's not something that any general meteorologist just learns in our studies in college, and because we don't typically use it on the job. There are specialized positions, meteorologists, that we'll talk about later, that actually focus all on space weather, and they know all this stuff. This is something new that I had to learn about, and I got to learn. It was interesting, but not something that we just cover on a day-to-day or any sort of meteorology program. So the aurora is formed, like I said, between interactions of these electrons, but really it's from the solar wind that's coming out of the sun, and it's impacting Earth's, what we call Earth's protective magnetic field, or magnetosphere. And so this aurora is just one manifestation of what we call geomagnetic activity, or these geomagnetic storms. And so as this solar wind increases in speed, and the interplanetary magnetic field embedded in the solar wind turns southward, then the geomagnetic activity increases. And when the geomagnetic activity increases, that's when the visibility of the aurora increases. So the aurora becomes brighter, more widespread, and what we call more active. So if we say the aurora is active, it's widespread, it's bright, it's moving. Whereas if it's not active, that we say it's not active when it's receding back towards the poles. Because when it becomes active, it extends south or north, whichever pole you're on. Now, the types of solar events that can cause this, and these solar winds that would cause a geomagnetic storm, there are two of them. And so the first one is called a coronal mass ejection, or CME. We have some pictures from our friends at NASA here of an example of some coronal mass ejections back from the year 2000. And you can see this is a pretty familiar sight for anybody who's ever heard of the term geomagnetic storm, because these result from these eruptions from the sun, or ejections from the sun. They're basically billions of tons of plasma that's being spewed from the sun at millions of miles per hour. So very, very fast. And when this CME does finally arrive at Earth, that is when it can produce some of the brightest geomagnetic storms. Compared to the next phenomenon we're going to talk about, these coronal mass ejection events will cause a brighter, more active aurora. Now, the second type of solar event that we can get more moderate-sized geomagnetic storms from is called a coronal hole. And again, I've included some pictures. They're the dark areas on these images of the sun. You can see the darker areas. They're called coronal holes. They are basically the source of high-speed solar wind streams. And when these high-speed wind streams arrive at Earth, again, they can produce active aurora. And like I said, these would typically be less active than the ones that we get from the CMEs. Oh yeah, that's the second point I already said. All right, next. Okay, so this figure, it is kind of tries to give you a zoomed out view, an idea of how this kind of works. And it's a little bit, it can be a little bit hard to grasp, but basically it's showing that this is showing the Earth with its magnetic field lines and the electrons that we talked about coming from the sun traveling down these field lines to the upper atmosphere. And then the green shaded area shows the shape of that oval centered around each pole. And that's the aurora that we talked about. It would be the same on the southern hemispheric pole. So like I said, I'm just looking through here. So again, the south and the north magnetic poles are bombarded with these electrons, and so it causes an identical aurora ring on both regions. All right, so these electrons we talked about, they're very fast moving and traveling about 1/10 of the speed of light, or 44 million miles per hour. And they're colliding with the atoms and molecules about 60 miles above the Earth in the upper atmosphere. And they're transferring their energy to the atmosphere, which excites the atom or the molecule to a higher energy state. And then as these atoms, then they're in their excited state, and then as they relax back to their natural energy level, they release photons. And these photons are finally what we actually see. So it's not the electrons that we're seeing, it's we're seeing these photons as the molecules and atoms are returning from an excited state to a relaxed state. Similar, again, to the process that occurs in neon or even fluorescent light bulbs. Oh, well, where'd it go? Oh, oops, this is my mistake. Click to the next one, see if it changes and pops up. There we go. I forgot this map was hiding another map. So this is the one I meant to show. So we have, if you know much about the Weather Service, you may know that we have specialized centers across the country for different phenomena that meteorologists will focus on. And so these, while meteorologists at our office and the other 121 forecast offices across the country do a little bit of everything, these offices are focused solely on things like the hurricanes at the National Hurricane Center, or just severe storms at the Storm Prediction Center, or in this case, just space weather. And so we have a space weather prediction center in Boulder, Colorado. And so these scientists are obviously focused solely on monitoring, observing, and predicting many types of geomagnetic events, but auroras and the northern lights are one of the things that they will forecast for. All right, so when we get to now moving on to predicting and measuring the aurora. So the electrons that we talked about creating the aurora also carry electric currents, which are conducted through the ionized portion of the upper atmosphere, which is called the ionosphere. Now these currents generate perturbations or changes in the magnetic field on the Earth's surface, and these apparent changes in the magnetic field can be measured. And that's where we get something called the planetary K index, or the KP, or KP for short. So if you've ever been looking for a aurora forecast, you might have been looking at the K index. That's a pretty common one. And so this is a measure of a good indicator of aurora and how active it's going to be. The location and the brightness of the aurora are directly correlated with the planetary K index. So when the KP index is high, which is between 7 and 9, the aurora is going to be bright, and the auroral oval, what they call it, will move to lower latitude. So the oval that is visible, that will be visible, will expand southward for us, southward to lower latitudes. And when we have, so that's when we have a 7 to a 9. That's what we really want. We want to see the aurora well. When we have a moderate KP index, which is a 5 or a 6, it will retreat towards the poles and be a little less bright, a little less active. And then wanted to note that even at lower levels of geomagnetic activity, like KP of 3 or 4, can result in some nice aurora with reasonable brightness and activity. It just may be harder to see, especially if you're anywhere near light pollution, that kind of thing. You might not be able to overcome the light pollution in where you are. So the Space Weather Prediction Center will issue forecast of the KP index and the aurora magnitude. So here's just an example of an aurora on the bottom right of an aurora forecast from the Space Weather Prediction Center. So you can see as it simulates the rotation of the Earth as it's the sunrise and the sunset is moving across the surface of the Earth. And this is just showing the case for Russia. But if we wanted to see whether or not the aurora would be visible for us, you could go to their website, watch their forecast, and see if on the next night, if that green, or especially if getting into the yellow and the orange, is anywhere close to where you are. And so the color is based on a probability scale. So the green it is anywhere from 10 to 50%, with the yellows to the red being over 50% chance of seeing the aurora. And then the map on the left kind of gives you an idea, a general idea, not hard and fast rule, but general idea of how far south you can observe the aurora based on different KP levels. So of course, I mean, it makes sense that if you're looking at the numbers on the right, so if you have a KP of 9, that's really, really strong. So you're going to be able to see aurora down as far south as the mid-Atlantic into even parts of Kentucky and Virginia. Whereas for us, we definitely, especially if you're in southern Mass, you'd want over something a 7 or over. But New England, anything from a 5 to a 7 is typically going to be good to have a good shot at it. All right, so when it comes to forecasting the aurora, the Space Weather Prediction Center can forecast different things at different time scales. They forecast in different ways based on the time scale. So starting at the small time scale, and we'll expand outward in time. So 15 to 45 minute scale. So by measuring the solar wind and the interplanetary magnetic field upstream of Earth, they can make really short-term forecasts pretty accurately with only a very small lead time. So you might be able to say, oh, if you wake up early to check and see if, 30 minutes from now, there's supposed to be a burst of some bright aurora, you can go outside with your camera. Now, when we're talking in, getting to an hour or more up to the day's time range, they can predict geomagnetic activity a day or so in advance just by looking for those solar corona holes that we talked about and the coronal mass ejections near the sun. And so if they spot one of these, they can track it and see as it leaves the sun, they can determine the path that it's going to take and if it will impact the Earth and at what time period. So this technique is more challenging, and the accuracy of these medium range forecasts is not as good. I would think it's a little bit similar to, as the farther out you go in time with these forecasts, similar to weather forecasts, you're getting farther away from the initialization point, which is just what's happening right now. Farther out you go in time, the more opportunities for errors to be introduced, so the more uncertainty there is. So the longer range or the medium range are a little less they're a little less confident in. All right, now we're getting into the really long range, 27 days. So these active regions on the sun and the coronal holes, they can stick around for long time. So talking many months as the sun rotates. And so as it does rotate, these active regions will repeatedly be directed at Earth, because as they're turning, they're going to, as long as they last, they'll eventually be pointed back at Earth. And so they will oftentimes produce similar levels of activity from one called solar rotation to the next. So that's a general idea. If there was good geomagnetic activity, good active aurora, in one instance, then 27 days later, then there's a good chance that there will be another instance of good aurora, plus or minus a day or two. So again, there is inherent uncertainty, but this is a good rule of thumb. Now then, when we talk about years, solar activity actually waxes and wanes on about an 11-year cycle. And so the geomagnetic activity and the aurora activity also follow an approximate 11-year cycle. All right, and then wanted to touch briefly on the different colors of the aurora, not get too deep into the weeds on this, but this image shows the typical auroral spectrum based on the wavelength. And so the different colors of the aurora are produced when different atmospheric atoms and molecules are excited to various energy levels. And so the most common auroral color is a pale green color, which is a wavelength of 557.7 nanometers. And so green is the most, I would have, even before I read this stat, I would have guessed green is the most common, because if you were to look across social media, other sites for aurora images, most oftentimes you see green. Red is far less common, blue is much less common, but green seems to be the one that everybody sees when they do see it. So yeah, count yourself lucky if you get to see any other colors but green as well. All right. Like I mentioned before, the Aurora Borealis and the Aurora Australis are mirror images of each other. That was kind of my biggest surprising takeaway from researching for this, that they mirror each other. And so when it's active in one hemisphere, it becomes active in the other at the same time. And also that the aurora exists nearly all the time. So it seems if you're not working at the Space Center, you're not always having your head in the aurora forecasting and observing, it may seem like, oh, the aurora pops up every couple of weeks or every month or so, and you hear about a big aurora light show, but actually it exists nearly all the time. And it can be seen somewhere on Earth nearly every night of the year. Now, you may be up in the Arctic or the Antarctic to see that, but somewhere on Earth. And so if it's a quiet aurora, it just consists of simple arcs running east to west across the sky at, of course, the very high latitudes. In the more active aurora, you will get those kind of curtain-like effects, and they look like they're dancing across the sky, and pretty amazing. And so this image over here, lastly, it shows the different phases of the aurora over the course of a typical night. So starting up in the top of the globe, up towards Greenland, Iceland area, you see the early morning. In the early morning, you'll get some patchy aurora. The aurora will be patchy. Whereas around midnight, it expands. So looking over the United States, around midnight, it expands southward. It will greatly increase in square footage, just of visibility. And then during the evening, you get some more quiet arcs. So of course, it kind of makes sense. It would be more visible at around midnight, when you're furthest away from that light pollution from the sun. All right, so some of the impacts, some surprising impacts that geomagnetic storms and aurora borealis related events can have on us on Earth. For one thing, it can impact our aviation partners. It can impact navigation and communication systems with planes and with people on the ground, including things like GPS, radio signals. All of these things that are tied into the Earth's magnetic field can be disrupted because of a geomagnetic storm. And so it's something that besides just getting some beautiful pictures, there is some real utility to being able to predict when and how strong and to what magnitude a solar storm is going to be approaching, because if we can lose satellite communication, we can have our navigational tools disrupted, and even surprisingly, our electric power grid can be impacted, and we can have problems with our electric power grid because of if it's a particularly strong solar storm. So lots of real life impacts from these, not just the pretty pictures that we see. All right, and that is my presentation. So hopefully you guys learned something, and if you have any questions at the end after Joe's briefing, we will be monitoring the chat and address what we know. Thank you.
All right. Thanks, Bryce. We do have a few questions. I'm not sure
Want
we'll
to
have
go
the answers
for
to
now?
them.
Yeah,
Yeah,
so I was gonna say, I'm trying to say we'll answer what we might know because
yeah.
this is a rare topic compared to the other webinars that we've done that we just don't know the details on this. I had to do a lot of research to make this. So a lot of this questions like is a solar flare considered to be a coronal mass ejection? I'm not sure about that. I'd have to get back to you on that. So yeah, so sorry, sorry if we can't answer them right now. But I did want to mention, I see somebody put in there, that's a good point. There are many websites for Aurora forecast information. There are lots of good ones out there. The Space Weather Prediction Center has one, and somebody put in and said spaceweather.com is a good one. Can't vouch for that one personally, but that's what somebody suggested. So check it out.
All right. And yeah, I see a couple questions from our friend Carrie too. Just we might be able to answer these. How strong of a geomagnetic storm would be needed for the aurora to be seen in Texas? Obviously, I'm probably
Oh,
going over 9, right?
yeah, over a 9 because the 9 got it down to like Kentucky. So I don't
Yeah.
know. I don't know how if it's physically possible.
Yeah, and she asked, has it ever gone higher than 9? I'm not personally sure myself.
I'm
It's,
not either. That would
I
be
would say it
something
would
I
be very, very rare if it has.
very rare.
But
Yeah,
yeah,
they only listed 9 on the Space Weather Prediction website. So I think it would be extremely rare for it to go over that.
yeah, there we go. And Ronald, actually, he's joined us tonight, our who contributed the photos from Rhode
Oh,
Island. And he just has a comment. I'll read this to you. He's an astrophotographer, and Bryce, you're a good photographer too. He would like to comment that even if a person cannot see the aurora with their eyes, it's important that people set up their cameras and capture photos because the
great point.
camera, either digital or film, will always capture the aurora. He says our eyes are not sensitive to color at night, so it would take a very intense aurora to be seen. Let me just catch the rest of that because it's blocked there. Hang on. Because it will always be, it would take really intense aurora to be seen. And let's see, with our own eyes. So that was it. Yeah. So actually, that's
That's a great point.
very good point,
Um,
Ronald. Thank you. Yeah.
the picture I showed from NWS Spokane, that one was much fainter to the naked eye. So that I did have a tripod set up, and so you have to keep the shutter open for a lot longer. I think it was a 30-second exposure, so that it can let in as much light as possible, so that it will appear more visible to you on film or on digital camera. So that's great point, Ronald. Thank you.
Yeah. Thanks, Ronald. Appreciate it. And you can check if you go to the Space Weather Prediction Center website, you can sign up for alerts too for the geomagnetic storms. I know you can get email alerts and for the larger when the activity is really picking up, and that'll help you as well if you want to have a chance to see the aurora. Of course, I think Bryce also a lot of our TV meteorologist partners always will
Yes,
include
they'll
that
share that a
information,
lot
and
if
we'll
there's
try and
one
include.
coming up.
We tend to kind of get it out on social media too, and let folks know. And just actually, we have a question from Eric, not a similar topic, but we put a lot of our science information on Twitter. We have our New England group that we put some various weather topics. We have our This Day in Weather History series. Eric was just asking any thoughts on adding content to other platforms because of kind of what's going on with Twitter, and really not at this point, Eric. Our social media program is managed on a national level, so we don't really have control as to what platforms. There was some talk about going to, we've been on Facebook and Twitter. There was some Instagram talk, but that really didn't work out too well. I think Bryce, they tested it.
Yeah, they tested it and they ended up not going with it. And so,
Yeah,
yeah, unfortunately, nothing would ever happen anytime soon as far as jumping to another. For now, it's just Twitter and Facebook, and we're just gonna ride it out and hope that it survives. Because
but
we
we'll
love
see.
posting. We love Twitter for posting and for getting reports and everything. So it's helpful for us during
Yeah.
storms.
We'll evolve as social media platforms evolve. So we'll
Exactly.
just, I guess we'll leave it
Can't
at
say
that.
right now.
All right. Well, we just want to, of course, wish everyone happy holidays too from all of our staff at the Boston office. On behalf of Bryce and myself, thank you for your support throughout the year of 2022, and we certainly look forward to bringing you more of these webinars in 2023 and beyond.